Welcome. This video focuses on modeling assumptions and concepts built into ideal lumped circuit element models, including resistors, inductors, and capacitors. The main meaning of lumped is no dimension, that is, no physical size at all. Each of the lumped circuit elements that the schematic symbols on this slide represent have no physical dimension in lumped element circuit analysis. These branch relationships for resistors, inductors, and capacitors illustrate the lack of dimension in lumped circuit element models. We see voltages, currents, resistance, inductance, capacitance, and time, but there is no indication of physical size in the branch relationship equations. The values for resistance, inductance, and capacitance certainly came from a physical structure with size and material properties, which gets idealized into the single constants R, L, or C. In ideal circuit elements, the resistance, inductance, and capacitance don't vary with time.
For an example of resistance R derived from physics, please see this book called First and Second for short.
SPICE simulation has ideal lumped circuit element models that use these branch relationships for both time and frequency domain simulations, steady-state frequency domain in this case. Beyond just ideal lumped circuit elements, lumped circuit analysis treats wires as ideal. Ideal wires have no length and no resistance, even when real wires might have resistance or parasitic series inductance at higher frequencies.
For an insightful look at connectivity with ideal wires, we recommend this video.
Real-world circuit elements are not ideal, and they often have parasitic quantities such as resistance or capacitance. How do we apply ideal lumped element circuit models like this ideal capacitor in practical real-world circuits? One way is to use multiple lumped element models to better model real-world practical circuit elements. Here we have a more realistic capacitor model where the equivalent series resistance is modeled along with the equivalent series inductance and a parasitic resistance in parallel with the other elements. Circuit element models including parasitic elements might be implemented in simulation like SPICE as subcircuits, creating hierarchy. Real-world physical circuit elements are not dimensionless. Practical circuit elements have physical size. How can we evaluate the validity of using lumped circuit elements in practical circuit design work? Instead of the pure notion of completely dimensionless lumped circuit elements with no physical size, we might say that lumped elements are small with respect to the wavelength of the circuit signals of interest. The higher the frequency of the signal, the shorter the wavelength becomes. Let's say that we have a sinusoidal current signal in a circuit. The horizontal axis is time. Zoom in to focus on a short section of the top of the signal. The short section of the expanded signal near the resistor doesn't vary much in amplitude over the representative horizontal size of the resistor shown. We want the circuit element size to be small in comparison to the wavelength of the signal in order for lumped element modeling to be valid and accurate. For a circuit element that is small, in comparison to the size of the circuit signals of interest, there is little or no variation in the value of the current within the lumped element resistor's physical dimensions. Similarly, the voltage across the lumped element doesn't vary along the dimension of the circuit element. At higher frequencies, shown by the sine wave in the middle, the wavelength becomes small relative to the physical size of the circuit elements. We have also answered a different question. How high in frequency are lumped elements valid? The answer is that it depends upon the physical dimensions of the circuit. Lumped element modeling, including SPICE simulation, is valid for frequencies as long as the wavelength is large in comparison to circuit size. There is no one single frequency limit value for all situations, and one must do consistency checks to make sure that the validity works in your application. When lumped circuit elements are no longer valid and useful for circuit analysis and design because of frequency, we can turn to distributed elements. Transmission line models, basic distributed circuit elements, can model variations in the signals along the dimensions of the transmission line. At higher frequencies, wires can be replaced with transmission lines in circuit design and layout.
To continue the discussion of transmission lines and distributed circuits, we recommend this video. Thank you for watching and learning with us.